lecture I will be talking about superstability. Consider the map u n plus 1 equals to f of un. Let's take Taylor expansion, use Taylor expansion for function f of u. Then what we will have, un plus 1 equals to f. We will take Taylor expansion around some value of u, which we will call u capital plus derivative of f over at u capital times un minus u capital plus half of second derivative at u capital times un minus u capital squared, and so on, other terms. Let u capital be a fixed point. Which means that u equals to f of u. And let u to be stable, which means that f, derivative of f at u by absolute value is less than 1. Now, under these two conditions, un tends to u capital. Then altogether what we will have? We will have, since un tends to u capital, and we can use linear approximation. So we will have un plus 1 equals to f of u equals to u, therefore we can put here u, plus f prime of u times un minus u capital. After taking u capital to the left hand side, we will have this equation. Now we replace the difference between un or un plus 1 and u capital by epsilon n, so it's substitution, it's new variable. And in terms of new variable, we will have linear equation. This linear equation. We know solution for this linear equation, it was derived before. Epsilon n is derivative of f at u capital to the power of n times epsilon naught, value of epsilon for initial value of epsilon. So this is epsilon naught is u naught minus u capital. This formula for epsilon n tells us that epsilon n is a geometrical progression, so it's a sequence for a geometrical progression. If so, un tends to u capital geometrically if this f prime or at u capital by absolute value is less than 1, so it's a property of geometrical progression. And what we can even state more, that close the derivative of f at u capital to 0, faster is convergence. And when f prime at u equal to 0, it is extremely fast. In fact, we should not consider, we should give up on the linear approximation, because this term this tends to be 0. But we will need to consider second order approximation given by this formula. Times epsilon plus n plus 1 equals to half times second derivative of f at u capital times epsilon n squared. And now we see that convergence when epsilon n tends to 0, then epsilon h next epsilon n plus 1 will get to 0 even faster than geometric. Let's see how it works in terms of logistic map. So we have logistic map now. Un plus 1 equals to r un times 1 minus un. We know that we have two fixed points, u1 equal to 0 and u2, which is 1 minus 1 over r. So our problem is finding a value of r such that u2 is superstable. So derivative of f at u2 should be equal to 0. We know that derivative is given by the formula r minus 2ru, and therefore derivative at u2, we derived it before, it equals to 2 minus r. And if we require for to be 0, we find out that r equals to 2. So what it means, when r equals to 2, u2 equals to 1 minus 1 over r, which is half, and it is superstable. Or un plus 1 equal to 2 times, now instead of r we put 2, un 1 minus un has a superstable fixed point. Eventually this map is a case when we can find analytical solution for this map. We can find analytical solution. So another case is r equal to 4. Also can be found analytical solution. Can be found. So to find analytical solution, we again introduce variable epsilon. Epsilon n is un minus u2, and in this case u2 is half, it's un minus half. Then our equation un plus 1 equal to 2 times un 1 minus un can be written in terms of epsilon as epsilon n plus 1 plus half, it is this, it's un plus 1, equals to 2 times epsilon n plus half, and this is 1 minus epsilon n minus half. This will be equal to 2 times epsilon n plus half times half minus epsilon n. This equals to 2 times, so this is sum, product of sum and difference. It will be quarter minus epsilon n squared. And finally, this is half minus 2 times epsilon n squared. So this equals to this. Half is common, therefore epsilon n plus 1 equals to minus 2 times epsilon n squared. This is what we got. Equation, difference equation in terms of epsilon. For n equal to 0, we will have epsilon 1 equal to minus 2 times epsilon 0 squared. For n equal to 1, we will have epsilon 2 equals to minus 2 times epsilon 1 squared, and epsilon 1 is here, minus 2 times minus 2 epsilon naught squared, and this will be minus 8 times epsilon naught to the power of 4. For n equal to 2, we will have epsilon 3 equals to minus 2 times epsilon 2 squared, and this will be equal, epsilon 2 squared is here, it will be equal to minus 2 times minus 8 epsilon naught to the power of 4 squared, or this will be equal to minus 2 to the power of 7 epsilon naught to the power of 8. And we can write it as minus half 2 times epsilon naught to the power of 2 to the power of 3. And this gives us following formula: epsilon n equals to minus half 2 times epsilon naught to the power of 2 to the power of n. So this is our analytical solution. Now, when we know epsilon naught, we can find epsilon n directly. And this is indeed faster than geometric progression. Fast convergence. Explicit formula. This formula can be proven using mathematical induction. Final remark, we can get back to our original variable un, which was half plus epsilon n. Then we will have un equal to half instead of epsilon, and we will put minus half 2 times epsilon naught squared to the power of n, and we can just simplify it like this. Half, can take half outside, 1 minus 2 epsilon naught squared to the power of n. So this is our formula, analytical formula for un. So it will be 2 times u naught minus half all of this squared to the power of n. Oh, and finally it is half 1 minus 2u naught minus 1 squared to the power of n. So this is our formula for un. If we know u naught, we can find un for any n.